be able to answer a few of these questions. I'm going to kind of refresh your brains a little bit. I want to see if you can finish these sentences. This would be based on video type material. So I'm going to say this. If G is concave up, then G double prime is probably positive. That's right. And if G double prime is negative, then that would mean that G is concave down. Okay, so some takeaways from the video. Sounds like maybe you have a good sense of what that was. So take a look at example number 2. Example number 2 says, given the graph of G prime. So it's really important that we always identify what the graph is that we're looking at, because if it's G, it means one thing. If it's G prime, it means something else. If it's G double prime, it means another thing. So it says, given the graph of G prime, determine the intervals on which the graph of G is concave down and increasing. Okay, so let's review a little bit. We're looking for these two things happening at the same time. One of these is actually kind of old. If I were to say, if G is increasing, then G prime is positive. Yeah, that would be a way to say that. I'm going to look at it from that perspective here first. If I'm looking for where G is increasing, I'm really looking for where G prime is positive. Where would that be located on that graph? Whenever that graph is where? Above. Yeah, above the x-axis. So if I were to just maybe highlight that, above the x-axis, any of those intervals that are above the x-axis, that would be where G is increasing. I'm going to switch colors here. Be where G is increasing. But then we're also looking for where G is concave down. And if G is concave down, then G prime is decreasing. There you go. That was another part of the video. Good job. So I'm going to highlight all the places where G prime is decreasing. So that would be here and there. So really, to answer this question, what we'd want to do is we would want to look for all the places that are essentially double highlighted. So my thoughts would be this. We would say that these two conditions are true on the interval -4 to -3. And what's the other one? 1 to 3, that's correct. So from 1 to 3, it doesn't ask us to give a reason for our answer, but I'm going to do that anyway. So I'm going to say because G prime is what? How would you finish that out if you were going to give a reason for your answer? Because G prime is positive and decreasing. There you go, good. G prime is positive and decreasing on those intervals. Okay, so one example there of what we could do with that. You guys have any questions? Okay. Next thing we're going to look at is points of inflection. Let's remind ourselves, we talked about this in the past. I think maybe this was in the video. A point of inflection is a location where the blank changes. Any ideas? Okay. Point of inflection is a place where concavity changes. So in other words, it's where the graph goes from concave down to concave up. It would be like right in there. Or concave up to concave down. Right in there. So those are points of inflection. It's where the graph kind of bends from concave up to concave down, or the other way around. Okay, so one of these we've already looked at in the past. We're going to look at both of these here. An inflection point on F happens when F prime changes from increasing to decreasing or decreasing to increasing. Another way to think about it would be to say an inflection point on F occurs where F double prime changes signs. Both of these are very useful, but I think if you were given a graph of F, you should use the first wording. You don't have to, but I think that that's best. If you're given information about F or F double prime, then we're going to use that second wording. Okay, so an inflection point happens when F prime changes from increasing to decreasing or vice versa. Inflection point on F happens when F double prime changes signs. Do you have any questions about either of those? I think the video covered those a little bit. But do you have any questions? Okay, so before we do this this next example here, I want to make one suggestion for you guys. I'm hoping that you watch the video and you're listening and we're all paying attention and all this is making sense. You're like, oh yeah, where F prime does this, then F does that, and all these things. But I hope you can admit or maybe realize that as time goes on, it's going to be pretty easy for these things to get all jumbled up, right? Well, if F prime changes from positive to negative, what does that mean? If F prime changes from increasing to decreasing, what does that mean? You can see, I think, I've seen it a lot, that it's easy to get these things mixed up. So I have a suggestion for you. Throughout each section in the notes and at the end of each note, there's key takeaways, right? My suggestion is this. If you wanted to work with somebody or just work by yourself, you could do this. If you wanted to make flashcards, or on one side of the flashcard it says, if F prime changes from positive to negative, and on the other side you said F has a relative maximum. Or you said on one side H double prime is negative, therefore H is concave down on the other side. Something like that. You could probably make a good 15 or 20 flashcards, to be honest with you. I would make those, and throughout this week and next week leading up to quizzes later on, I would constantly be doing these, flipping through these flashcards. And it kind of goes both ways, right? You could look at one side and think of the other side, or you could flip it around and do it the other way. You could do it with a friend. You could even say, Neil, you're my friend. Would you like to make some flashcards with me? Why don't you make 10 flashcards you think would be challenging? I'll make 10 flashcards that I think would be challenging, and we switch or we share or we work on them together. Something like that to really challenge each other and to just kind of have those. If I were you, I'd put them in my pocket or my bag, and when I'm sitting there waiting in lunch, the lunch line, to get a burrito or something, flip through 5 flashcards, When I am standing by the door at 6:50 and I forgot my card or whatever, or the card doesn't even work to get in the building, sit there and flip through some flashcards for 5 minutes. If you did that, if you made use of your time like that, you would have it, right? You would get it instead of getting to a quiz later on and being like, F double prime change signs, and I have no idea what that means. I know it should mean something, but I don't know what it means. If you've done those flashcards, you could do something more high-tech, those of you that are programmer types, but I'd make 3x5 cards. That's just me. Okay, that makes sense? Encourage you to do that. All right, so example number 3 says find the points of inflection and discuss the concavity of the graph of, what information did I give you? Did I give you F, F prime, or F double prime? F. So if I give you information about the graph of F, then I think personally it's going to be easier for us to look at the graph of F double prime or information about F double prime to answer a question like this. So if I'm supposed to use the graph of F double prime or the equation for F double prime, I probably should have it, and I don't. So how do I get from that to F double prime? Derivative and then derivative. Yeah, just do it twice. Okay, so see here, it would be F prime equals 6x squared minus 6x minus 12. F double prime equals 12x minus 6. Okay, so we found F double prime. And we're looking for where we have points of inflection. So points of inflection will happen when F double prime does what? Changes signs, right? So where F double prime changes signs. So if I'm looking for F double prime changes signs, where might I want to look? 0. Yeah, where F double prime is 0. That should give me a hint about where F double prime will change signs. So I'm just going to go equals 0. Remember, that's a really important thing to write. If I do that, I get x is equal to 1/2. That's right. Okay, so x equals 1/2. That is my potential inflection point. We do need to test this out. Can you think of a way that we could test this out? A graphic, yeah, a sign chart, right? So this is not going to be an F prime sign chart. This is going to be an F double prime sign chart. So I'm going to put F double prime there, put 1/2 there. Now there is such a thing as an F prime sign chart. We've used that before. That is useful. It does stuff that we want it to do. We don't really care about that right now. We want to know about an F double prime sign chart because, again, like you guys said, we're looking for where F double prime changes signs. Okay, so on the left interval, what would you all suggest for a test value?
0.
All right, and when we do that, what do we get? -6, and on the right, what would you plug in?
1.
And when you plug that in, what do you get?
6.
Okay, so check it out. F double prime actually did change signs. Word of caution, depending on the nature of the function, sometimes F double prime won't change signs, even given these similar circumstances. So you do want to test it out and make sure that that really does happen. All right, so we can say then that, based on our reasoning, F has an inflection point at x equals 1/2 because why? F double prime changes signs, yep. So F double prime changes signs there. Sorry. Oh, sorry, I wrote in the bad spot there. Okay, and it does say discuss the concavity, so let's discuss the concavity. We really can just use this little sign chart that we used earlier to help us discuss the concavity. Let's just do this verbally. So if I were to ask you for intervals where F is concave down, what would you say? Yep, the whole left side, right? Negative infinity to 1/2. Because why? Yeah, F double prime is negative on that interval. And then, of course, on the right interval, F double prime is positive, which means that F is concave up. What was the little thing on the video that I used to kind of help you remember this? The crazy faces, right? The smiley, scary face and the sad, scary face. They're both sort of scary. Yeah, the faces. All right, any questions on example 3? Okay, good deal. Let's move ahead. All right, example number 4. This brought up some interesting discussion in the other class. Let's see how this goes for you. It says, given a graph of f prime, determine the inflection points of f, and we're supposed to justify our answer. So let me just remind you, you're given a graph of f prime here. For those, if you're like me, especially, when I was learning this stuff, I really had to be very careful that I made special note of what I was given, because it was really easy for me to just assume that everything was whatever I was assuming it to be. On a different day, it seemed to be a different thing. There was no rhyme or reason to it. And so I found myself always marking and saying, okay, this is a graph of f prime, and then I'm going to try to reason from that instead of assuming that it's something else or not even acknowledging that it's f prime and mistakenly calling it something else. So maybe mark it up and be like, okay, this is f prime, draw an arrow to it, underline it, whatever, make a big deal about it. Based on that, we're supposed to determine the inflection points of f. So if you need to peek back, there was that reasoning based on f prime. So if you want to kind of look back or if you just remember it, that's great. We want to use that kind of reasoning based on f prime to help us determine the inflection points of f. And I'm going to let you guys try this one on your own for a couple of minutes, and we'll check your answers in a little bit. So there are 2 of them, and the 2 inflection points occur at x equals -1, and the other one is at x equals 2. And most people have very little issue with x equals 2 because they can say, hey, look, based on what we talked about with inflection points at x equals 2, doesn't f prime go from increasing to decreasing? And it happens nice and smoothly. Almost nobody has any issues with that. But there are some times when people have issues with x equals -1. Why would somebody have an issue with that? It looks like the proverbial doink point, right? The sharp point thing. And they're going to say, wait a minute. And they'll say, it's not differentiable, or it doesn't exist there, right? We want to be really careful with the word it because it could mean all kinds of stuff. So you are correct that something is not differentiable if you were to say that. Specifically, what is not differentiable at x equals -1? G prime, or is it f prime? Yeah, f prime. F prime is not differentiable at x equals -1. Completely agree with you. So what does that mean about something not existing? What doesn't exist? F double prime doesn't exist at -1 either. So then what we do is we'll take that a little too far and we'll be like, and therefore there's no inflection point on F at x equals -1, and that's where you go wrong. So here's what happens. If you look at this graph of f prime, can you see, I just have to do this visually, can you see that the graph of f prime right there is continuous? Right, there's no jumps, removables, or vertical asymptotes, right? So at least on that interval right there, the graph of f prime is continuous. And if the graph of f prime is continuous, that actually guarantees that f is differentiable. Remember if f is continuous, or differentiability implies continuity, all that stuff? Yeah. So if this graph of f prime is continuous, that means that f is differentiable, which means that at x equals -1, f would be nice and smooth. And so it very easily could have an inflection point. So this would be a point where people would, I think, justifiably ask, okay, that's neat and everything. What in the world would f look like if that's f prime? Or what kind of a function is that? That make sense? Anybody know? What kind of a function would f have to be if that's f prime? It's really only one thing it could be. It might be involved, but overall, there could be, I'm going to give it away if I say too much. Yes, Matt?
What do you call it when it's like the bracket? There's like x is less than 1 here, and x is greater than 1.
Piecewise. Piecewise. It would have to be a piecewise. Right? Do you see there's, I see maybe 4 pieces, 3 or 4 pieces up there? So with a piecewise, do you remember those questions we did in the past where it gave you the piecewise thing with the bracket and all that stuff, but then like inside there it was like ax plus 7 and bx squared minus 9, and the question said find a and b so that this function is continuous and differentiable everywhere. Do you remember those questions? If you don't, make sure you do for your loop quiz. But with those questions, remember we found the a and the b, we made it nice and smooth and continuous and differentiable everywhere. If you started like differentiating that, it would eventually fall apart like this. You would start to get points of non-differentiability, and eventually you'd get some jumps within that piecewise derivative set. And so this would have to be piecewise, but f would be nice and smooth and continuous because f prime is continuous. Okay, so does that answer your question, Baxter?
Well, I was just thinking of f double prime.
Yeah.
At -1.
Yep. There'd be a jump.
Yeah.
There would definitely be a jump.
So you were given like f double prime, question that had that, and
yeah, it would still be okay. So remember the other definition of inflection point is where f double prime changes signs.
right,
So at -1, x equals -1, f double prime would jump from a negative to a positive,
even though it doesn't.
and it would change signs.
Even though it doesn't exist at those points.
Correct. Yep. And it's all based on the whole piecewise idea. Yeah. Okay. Excellent questions. Okay, so we would say those two places are where f has an inflection point because it did say justify your answer, so we're going to say because f prime goes from decreasing to increasing at x equals -1 and the other way around at x equals 2.
So we can't use f double prime.
You could. So if you said, yeah, you sure could. So if you said, unless I said use f prime to argue, then you couldn't. So what did you say? So you said x equals -1, x equals 2 because?
It switches from negative
It?
to positive. I think, well, I said f double prime switches.
Yeah, so that would make all the difference, right? So if you said because f double prime does what?
Switches from negative to positive at x equals negative.
Or the other way at 2? Totally fine. Totally fine. And what he's doing, of course, is you're basically saying, hey, the slope of that graph is f double prime, right? And that's good reasoning, for sure. Okay, anybody else? Okay, fantastic. Let's look at our last example like this, example number 5. I can't quite fit the whole thing on the screen. You've got it in front of you. So I think that you can answer, if you can answer A, you should be able to answer B. So let's kind of work on A and B together. It says identify the intervals in which the graph of H is concave up, or B, where H is concave down. So please take a minute here, and please notice, just like I mentioned before, that you are given a graph of H double prime, not a graph of H prime or H or anything like that. You're given a graph of H double prime. So that means you need to reason from that and hopefully come to a good conclusion about H. So that's a graph of H double prime. So we're actually looking for H double prime is positive. No, positive. If H double prime is positive, and that'll come into play later. Yeah, if you're looking at C, yeah. So we're looking for H double prime is positive. So it'd be anything that is above the x-axis. So I would say from -4 to -2, along with 3 to 4. Your justification would be because h double prime is positive on those intervals. Does that make sense? Okay, then the other one is identify the intervals on which the graph of h is concave down. So here, we would be looking not for where h double prime is positive, but for where h double prime is negative, and that would be below the x-axis. So there's two different ways I would take this answer. If you put negative 2, 3, that interval right there, I would give you full credit. Or if you decided to do this, negative 2 to 1, along with 1 to 3, I would give you credit for that as well. Do you see how when x is 1, it looks like h double prime is 0 for just like 1 point? So sometimes people will write it like that. I think you're going to find most textbooks are going to like this one better because concavity can really only be judged between any 2 points. And it's true that h double prime is 0 when x is 1, but you can't have concavity at 1 point really. It really has to be between 2 points. And so it's true that h double prime is 0 at 1 point, but on all the other points around it, h double prime is negative. And so that's why they would probably like that one on the left better. But I would give you full credit, and the AP reader would give you full credit for either one of those answer sets. Of course, your reasoning would be because h double prime is negative, or you could say less than or equal to 0 on that whole interval, depending on how you wrote your intervals. Okay? All right, and then the last one was inflection points. So, yeah. So how many inflection points did you see for h? 2, and they happened where? Negative 2 and 3. I agree with that. So I'm just going to put this over here. X equals negative 2, x equals 3. What about x equals 1?
But it doesn't change signs.
That's the thing. That's the confusing part. At x equals 1, h double prime is 0, but it doesn't change signs. H double prime has to change signs in order for h to have an inflection point. And obviously it's very close at 1, but it doesn't. H double prime does not actually change signs. Is that good? Okay, so justification-wise, you would say because h double prime changes signs there. And that would be it. All right. Any follow-up questions? Okay. So the last thing we're going to do here is we're going to set the stage for our final example in 3-4. So tomorrow what we'll do, we're going to do a little bit more right now, but tomorrow what we'll do is we'll do our one example that will be remaining, and then we'll be doing quiz review after that, and we'll kind of just see how long that goes, and then we'll decide from there what we'll do. Okay? So let's take a look at our last little bit here. Right here. I do want to say about this second derivative test. The second derivative test is not required for the AP test. However, it is very useful. And if you look back at some of the old like AP test, like rubrics or solutions, you're actually going to find that the College Board themselves will use the second derivative test from time to time because it's easier in some cases. And I think you'll find it easier too. So even though this is not part of the curriculum framework, I am going to do it here because I think it could actually make your life easier at times. It won't always make it easier, but certain situations it will. We'll talk about those situations next time. I thought I would just lay some logical groundwork for this before we leave, and then we'll pick this up again tomorrow. So let's remind ourselves what all this means. So it says, let f be a function such that f prime of c is equal to 0. This means that c is a critical number, critical point. Yep. Okay, so you've got a critical number. It's where we've got a horizontal tangent line. So here are the 3 parts. The first part says this. If f double prime of c, so in other words, at the critical number, f double prime is negative, that would mean that f is concave what? Down. Agreed? Okay, so then let's be logical about this. If you've got a critical number at a place where f is concave down, then f has to have a relative max. Yes. And that's what this picture is intended to illustrate. You've got a concave down portion of the graph. So anytime on a concave down portion you have a horizontal tangent line or a critical number, then it's got to be at a relative max. It's got to be. The other way has to be true as well. You still have a critical number at C, and if f double prime of C is positive, then f has to be concave up. And if you've got a critical number at a place where f is concave up, then we have to be having a relative minimum. Yep, you can see that on the graph as well. Concave up, horizontal tangent line, it's got to happen at a relative min. If those two things are true, it's got to happen at a relative min. And then the last piece of the puzzle is right here. If you find you've got a critical number at C, and then you try it out in the second derivative, instead of getting f double prime of C being positive, or f double prime of C being negative, you get f double prime of C equals 0. That means that the second derivative test fails. It just doesn't tell us anything at all. We can't assume anything from that. We just have to say, well, I don't know what that is. And so instead of using it, I have to use the blank, blank, blank. The first derivative test. The first derivative test will never fail. But in some cases, and so you might say, based on that, why would I ever use the second derivative test? You might use the second derivative test in certain cases because it's simply faster. In certain cases, it's going to be way faster, but the first derivative test is old reliable. If second derivative doesn't do anything for you, you go back to the first derivative test and it'll work for you. We'll practice one of those when I see you next time. Have a wonderful rest of your day. See you guys.